Right, here we go. Last full week of classes. Again, hope everything's going well out there. Just want to encourage you to press on. Please reach out if if you need some help, if you have any questions. Always here to help. I really enjoy answering your questions. That's why I give you multiple opportunities, multiple venues in which you can come and ask. And even if those don't work, please continue to ask, continue to reach out. We still have a couple weeks left here, including finals week. Don't forget that tomorrow is the project due date. You can avoid taking the final by doing that last bonus question. I've already noticed that some of you have taken advantage of that and done a good job. To me, it was just worth it to have you work through that. And if you could push through and see what was happening, you're going to have to penetrate the depths of a lot of things. And I think it was worth your while. I think those of you that did it would agree. So we will have one more homework quiz. I will likely send that out on Wednesday. We do on Friday. And today I want to do one more thing in chapter 7. And then we'll move on to chapter 8 and do a couple of things with limit theorems. Maybe spend a couple of lectures on that and we'll be done. That's it. Okay. All right. So let's take a look at this. Last time we ended by looking at the moments of the number of events that occur. This was kind of a bizarre thing to consider, but I want you to see why it's useful. Okay. So, or at least it seems a bizarre thing to consider, but it indeed ends up being really, really useful. So give me any events, okay, A1 through AN, that could be highly dependent. Okay, so I just have n events, and I let x be the number of events that occur, and then I write x as the sum of the indicators of these things, because indeed that is the number of events that occur, right? It's 1 if ever an event, one of those events happens, and 0 otherwise. So clearly that sum is going to count the number of those n events that actually occur. The expectation of that thing is just the sum of the probabilities of those events, as we discussed. And then we kind of finished by asking, what if we wanted to look at pairs of events instead? We want to know the expected number of pairs of events that happen. Pairs of events. I mean, by pairs, I mean unordered pairs, okay? Just like 2 sets of events. And I don't care about distinguishing A1, A2 from A2 to A1 or something, okay? So we looked at that and we came up with the following, okay? So for I less than J, AI intersected with AJ happens if and only if the product of those 2 indicators is 1, because they would both have to be 1. And so that means that both those events happen, which means the product of those 2 indicators is just the indicator of the intersection of those 2 events, okay? And so that led us to the realization that if I want to look at the number of pairs, right, 2 sets of events that happen, well, on the one hand, that's x choose 2, because x was the number of events that happen, and I'm just choosing 2 of them that happen to occur. Then that has to be equal to the sum of those indicators of pairwise intersections, because that sum is going to count the number of pairwise intersections that happen. Okay, so those have to be equal. So the expectation of x choose 2 is going to be like if you just push the expectation through the sum, the probability of those intersected pairs of events. Okay, and if I wanted the second factorial moment, okay, then I could just multiply through by 2 factorial. And I end up with that formula, 2 times the sum over I less j probability of the ith event intersected with the jth event. Okay, and let's see, we ended with this. We said, well, hey, what's stopping us? Why not 3 sets of events? Well, whatever x is, that's the number of events that occurred. I would just have to choose 3 of those, okay? So that's the total number of 3 sets of events that happen, okay? And by the way, this is events, not just any old events. Events that, well, let me see here. Let me do this. Events what? Events that happen. Okay. 3 sets of events that happen. Okay, well, actually, this is a question. Okay. Well, by the same reasoning we did before, it's going to be the sum of overall I less j less k, the indicator of that triple intersection. So the expectation of x choose 3 is the sum of the probability of those triplicate intersections. So the expectation of the third factorial moment, and I want to make sure that you know that terminology. This is the third factorial moment. Okay. Third factorial moment is just 3 factorial times the sum of those the probabilities of those triplicate intersections. And in general, here's the formula for the kth factorial moment. And I remarked that the factorial moments, if I know them all up to level k, I can take combinations of them to get the ordinary moments. Okay, because like the second factorial moment is just, you saw that on the previous slide, we wrote that down. Second factorial moment, which is down here at the bottom, is just the expectation of x squared minus the expectation of x. Okay, we know the expectation of x from just from before. That's just the sum of those probabilities. Okay, so I would be able to get the expectation of x squared by having the first factorial moment, which is just the expectation of x, and I would add that to the second factorial moment. Okay, and by the same token, I would be able to get my hands on the the third moment of x, expectation of x cubed, by using the third, second, and first factorial moments. Okay, so hopefully that's clear to you how you could kind of recursively get all the moments of x from the factorial moments, from the subsequent factorial moments. Okay, taking combinations of those. All right, so I want to use this in the context of the binomial distribution. So here's example, x distributed as the binomial with n trials in proportion of success p. Okay, how are we going to define our AIs here? Well, AI is going to be equal to the event, the ith trial is a success. Okay, so you know that this binomial distribution is the number of successes in those n trials, yes? So we've already talked about this, but x is going to be the sum, I going from 1 to n, the indicator of AI, okay? Because it's basically, it's the number of events among A1, AN that happen. Okay, so literally this exploration we just did is tailor-made to deal with this binomial situation, just flat out. Okay, so that's good news for us. And by the way, the hypergeometric can be looked at similarly. Okay, so there we go. So we already know, look, if you want to do this again, I guess that we can. So what is the probability of AI? That's easy, okay? So the probability of AI, that's the probability of success on the ith trial, and that's just P by definition, okay? So the expected value of X is just going to be the sum I going from 1 to n of P every single time, which is just NP. Boom, okay? There it is, okay? So let's think about this. What about the factorial moments? Okay, well, we know that the expectation of x falling k is going to be k factorial sum times the sum I1 less than all the way up through ik. The probability of AI1, or yeah, AI1 intersected all the way up to AIK, okay? That was the formula we came up with before, okay? Well, what is that? Well, these events are independent, okay? These events right here are independent. They're independent. That's one of the assumptions in the binomial distribution. So what is this probability? Well, it's going to be the product of all those probabilities of various AI, A sub I sub j's, okay? So, but all of those are just p, and there's k of them. So that's like p to the k, all right? So look at this, I'm summing up a bunch of p to the k's. Are you serious? Okay, so I'm adding p to the k itself for every single k subset of indices I can get. Well, how many k subsets are there? Okay, well, that's easy. Just n choose k. Right, so this is equal to k factorial times n choose k, right? Because all those k subsets, okay, times p to the k. All right, which is equal to, okay. Look, I mean, if you think about it for a second, k factorial is going to cancel the k factorial downstairs. N minus k factorial is going to cancel, you know, a bunch of factors upstairs, and you're just going to end up with n falling k times p to the k. Look at that. We just straight up figured out what the k factorial moment was for the binomial. That's amazing. Okay? Just that easy. We were able to find all of the k factorial moments, which means we can get our hands on all the moments for the binomial. Do you remember how hard we had to work just to find, like, you know, like the variance of this thing, which only involved the second moment of the binomial and the first moment? We just found all of them that quick by being willing to kind of look at this thing as a sum of indicators, okay? And by the way, there's another way to do this, okay? There is another way to do this. Oh, by the way, let me just to show you, okay? So note, let's just write this down. Okay, once again, the expected value of x falling 2, well, that's just, you know, that's going to be n falling 2 times p squared, okay, apparently, from the previous line, but that's also equal to the expectation of x squared minus the expectation of x, okay? And of course, we know that the expectation of x is equal to np, okay? So let's see here. What does this tell us? So the variance of x is equal to the expectation of x squared minus the expectation of x with the square on the outside, which, by the way, is equal to the second factorial moment, okay, plus e of x, because I need to get rid of, right, I need to get rid of this annoying thing right here by adding the expectation of x in, okay? And then I'm going to subtract the square of the expectation. Okay, so what do I get? Well, I'm going to get n falling 2 times p squared plus np minus np quantity squared. Okay, which, by the way, I can get a factor of np from all of these things. What's left behind from that first summand? Well, that's going to be n minus 1 times p plus 1, okay, minus np. Okay, and notice that there's going to be some nice cancellation that happens here. So this np, if I distribute this p in here, I'm going to get an np that cancels with that, and I'm just left with 1 minus p. Hey, check it out. We got it again. np times 1 minus p, which is npq, okay, which is our well-known variance formula at this point. Yeah. So remember before when we actually wrote x as a sum of indicators. In the case of the binomial, we ended up finding the moment generating function fairly easily. But there's one other kind of function that I want to introduce you to. Okay, so and I'll do it in the context of the binomial just because it's useful. Okay, so let me just say the moment generating function of x, which is the binomial NP. Okay, so remember this is mx of t, which is equal to the expectation of e to the tx. I'm just going to go through this again because it's super important, okay, that you be able to be comfortable with this. So this is the expectation of e to the t indicator of a1 plus dot 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 plus indicator of an, okay, which is going to be when I distribute that thing through, it's going to be a product of these things. Expectation e to the t indicator of a1 dot dot dot, because these things are independent. That's why I can do this. Expectation e to the t indicator of an. Okay. Yeah. So what's this going to be? Well, the indicator is 0 on the complement of the event a1. Okay. So e to the t times 0 is 1, and that's going to be probability 1 minus p. So this is 1 minus p plus, well, let me write, okay, so hang on. Let me be a little clearer, okay. So this is q, right, 1 minus p, that's where this thing is 0, plus the probability of a1 times e to the t, so that's just p e to the t, dot, 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 p, or q plus p e to the t. A total of n times, right? So we get q plus p e to the t raised to the n. Okay, and that was helpful to us, I think, right? So one way that we could have gotten the factorial moments, well, actually, no. This would be sort of nasty to get the factorial moments, unfortunately. Okay. But there's another thing. So this is the moment generating function. There's also something called the probability generating function of x, okay? And I'm going to do it in the case of the binomial, but this applies generally. So this is defined by px of t, and the book doesn't really spend much time talking about this at all, okay? But this comes up a lot. So what this is it's just t, or it's the expectation of t to the x, okay? T to the x. So when you think about it, that's just what you get if you plug in logarithm. That's just what you get if you plug in logarithm of t in for t into the moment generating function, right? Because if I plugged in, think about it. If I replaced t with logarithm of t, right? Instead of t, I had logarithm of t right here. What is e to the logarithm of t going to be? Well, t, excuse me, and that would be raised to the x. So this guy is actually equal to the probability generating function is the moment generating function with t replaced by logarithm of t, okay? And when you do that, you can kind of see, I mean, I could have gone through the whole rigmarole of writing x as a sum of indicators, splitting up the thing into a product of things, but I can just straight plug in, I could straight just plug this thing in right here and get what we need. Yes? Okay, so let's see what happens here if I do that. So watch. This is going to be equal to Q plus what? PT raised to the n. Now, why in the world would that be more helpful in this case? Well, if you start trying to take derivatives of the moment generating function, it gets nasty. I don't know if you remember, but we had to do a bunch of nastiness because the chain rule was invoked, and we ended up having to do a whole bunch of junk with like, we ended up having to do a whole bunch of junk with like, the chain rule and the product rule, and that was super annoying. Okay, but in this particular case, look, we have this nice form right here, and we are going to have to invoke, the so-called. We're going to have to invoke the chain rule again, but it's going to be fairly easy. But let's look at this for a minute. Okay, let's look at this. So again, px of t. So x is still the binomial, just so that we're clear. Okay, and this is not in the book, but it's just something that I know to be very, very useful. So the probability generating function of this thing is given by q plus p t raised to the n. And by the way, the general form of the probability generating function is just going to be sum over all possible x's. Think about it, right? Because you know that this is going to just be the expectation of t to the x. So you know that this is like, this is equal to the sum over all x, okay? Or, I mean, if you're in the continuous case, it would be a little bit different, but it's mostly useful in the discrete case. So sum over all possible little x values, t to the x, so it's the probability of x, t to the little x, okay? So if you kind of think about this for a minute, one thing that you notice is that this right here, I could actually invoke the binomial theorem. The probability generating function, you know that the coefficient, because look at this, the coefficient of t to the x is the PDF. So the coefficient of t to the x is the PDF, the probability density function, p of x. Okay, so that's useful. It just kind of stores the probabilities right there. That's what I meant. Remember back a while ago, I said the MGF tells you everything about the distribution. The reason that is you can take the MGF, you can straight plug in logarithm of t, and then you can extract the probability. You could extract the probability distribution straight from that by just figuring out what the particular coefficient is. Now, if you think about this for a minute, look at this. This thing's going to collapse before our eyes. So this is just sum x going from, look, I'm going to use the binomial theorem here. That's why this is called the binomial distribution. So I'm going to use the binomial theorem. It's x equal to 0 up to n choose x. Okay. And what's it going to be? Well, it's going to be pt to the x times q to the n minus x. And look at that. Right, let me just rewrite this. This is just sum x going from 0 to n. I'm going to write it right underneath the general form of this thing. X going from 0 to n choose x, p to the x times q to the n minus x times t to the x. Therefore, this thing sitting right here, this thing, the coefficient of t to the x, that has to be p of x. Right, we got that through just a purely algebraic maneuver. We didn't have to think about it. It just automatically came out, and there's the distribution sitting right there. Now, if you don't think that's amazing, I don't know what to say. It is. It's amazing that we didn't even have to think about the distribution itself, except for the individual trials. And this thing just kind of pops out right there. Okay? So that's interesting. Another thing I would say is the following. Watch. Derivatives of this are quite easy. So px prime of t What's that going to be? Well, it's going to be nq plus pt to the n minus 1 times p. What about the second derivative? Well, fortunately, this is much easier than the moment generating function because I don't have that annoying factor of e to the t that came along for the right. The derivative of q plus pt is just p. It's a constant, okay? So what do I get here? Well, this is like, what is it? Well, it's going to be n times n minus 1 q plus p t to the n minus 2, and I have to multiply by the derivative again, so I get p squared, okay? And notice, think about this for a minute. This is just, if you kind of think about the expectation formula up here, okay, what's going on? It looks like the power, like if I took the derivative of that, think about this formula right here, okay? The power would come down, it would be x, p of x, t, x minus 1. So that's just the expected value of x, t to the x minus 1, yeah? What do you think this is? This is the expected value of x, x minus 1, t to the x minus 2, right? So the reason I'm showing you this is, I mean, think about it for a minute. What am I going to get if I plug in t, what am I going to get if I plug in t equal to 1? Well, if I plug in t equal to 1, I'm going to get the expected value of x in the first derivative. Okay, and I'm going to get the expected value of x times x minus 1, the second factorial moment, if I plug in t equal to 1. So let me just note that if I take the px, okay, if I take the kth order derivative of this thing, what am I going to get? Well, you can kind of see what's going to happen. It's going to be n falling k times q plus pt to the n minus k. So hang on a second here. So when I took the second derivative, it was n minus 1. So yeah, it's going to be n minus, this power and this thing, oops, that should be n minus 2. Sorry about that, n minus 2. So that power is always 1 smaller than the last thing in the product of n's downstairs. So the last thing in that product for the n falling k is just n minus k plus 1. So this is n minus k times p to the k, okay? And this is going to be the expected value of x falling k, t to the x minus k. So what is the punchline here? Well, I can actually get the expected value of the kth factorial moment from the probability generating function. And you know that you can use these to get at all the moments, okay? So this is going to be the probability generating function, kth derivative, evaluated at 1. And actually that's true no matter what distribution you're dealing with. The same, general principle is going to apply for those also, okay? So the kth derivative of the probability generating function evaluated at 1 is equal to the kth falling factorial moment. And if I plug in 1, n for t, look at this, it's going to be q plus p, but what's that? That's just 1. So this is going to be n falling k times p to the k, once again, okay? So we see that thing come full circle again. What else could we possibly do with the binomial at this moment? It seems like we know just about anything that our hearts could ever desire as it pertains to the binomial. All right. One more topic in this interesting little chapter. I want to talk about conditional expectation, because this is a topic that I have encountered a massive number of times in my career in sort of unexpected ways. So I want to make sure you're prepared to handle it should it arise, okay? So we've already talked about conditional densities. Okay, and I'm just going to do this in the discrete case, although it's not all that different in the continuous case either. So the probability of x given y at x given little y, okay, which is the value y, is equal to the probability that capital X, the random variable capital X, equals little x given the random variable capital Y equals little y. And we define that, or actually this isn't a definition, this is just what it is. It's the joint density of x and y evaluated at the point x comma y. And we are now imagining ourselves being on the event capital Y equals little y. So that means we need to divide by that probability. Okay, so we need to see what the joint density P of xy takes up of the on the sub sample space where capital Y equals little y. So that's why we divide by the marginal of y at little y. Okay, so yeah, and we have this expectation of the random variable x given that the random variable capital Y equals little y. So what would make sense there? Well, we would just compute the expected value of x, on or in our cognition that y equals little y. So we're given the information that y equals little y. So we weight all of those x values with the probability that x equals that on the event y equals y. Okay. So this formula ought to make sense to us, right? So hopefully this formula right here makes sense. We're just basically working under the assumption that my probabilities all must now be computed under the assumption that we're on the event capital Y equals little y, okay? Now, this right here is the thing that I want us to consider together. What do I mean by the expected value of x given y? Okay, the expected value of x given y, not y small, like a specific value, but the random variable y itself. Well, this thing is meant to capture all of these, right? So these things capture all of these, okay? So that is, if we're on the event y equals little y, capital Y equals little y, then that expected value of x given capital Y is just going to be whatever it would be if y was equal to little y. So in other words, expectation of x given y is itself a random variable, okay? And when you do computation with this, what you do is you kind of treat the random variable y as if it's like a constant or something, okay? Because you're given the value of y, so you might as well sort of treat it as such, okay? So hopefully that makes sense. So this thing is itself a random variable. The expectation of x given the random variable y is itself a random variable. And therefore we can ask questions like, what's the expected value of this thing, right? This thing takes on different values depending on what the value of y happens to be. It takes on different values, okay? So here is a little proposition for you, okay? So here's a proposition. I claim that the expected value of x is just going to be the expected value of this random variable, okay? I claim that it's coming, right? Because this, after all, is a random variable, right? That takes on different values depending on what y is, okay? Depending on what y is. Okay. So what's going on with that right-hand side there? So let's actually try to prove this thing, okay? What we're going to do is we're going to just sort of unravel the right-hand side and show that in the end we actually do just get the expected value of x. Okay, so let's have a look at that. So what is the expected value of x given y? Okay, so let's just write it out. Expected value of the expected value of x given y Okay, well, this thing takes on different values depending on what y is, right? So this is like the sum over all possible y, the expected value of x given, right? We know that if we're on the event y equals y, it's just going to be the expected value of x given that y is equal to y, but we have to weight this by, because this is an expected value after all, the probability that y is equal to y, okay? Probability that y is equal to y. Now, what's this? So this is going to be the sum over y, and then I'm going to just use the formula that was on the previous slide here, or the previous board. I'm going to actually use this formula right here. Okay, use this formula right here, and we're going to be able to get what we need here. So let's check this out. Okay, so what are we going to get? It's going to be the sum over x, or the right sum over y, sum over x. Okay, and it's going to be x times the probability, right? Because I want x is the random variable, so that value times the probability that x is equal to x, given that y is equal to little y, we're working under that assumption, times the probability that y is equal to y. Y is equal to little y. Okay, so what is this though? I mean, for crying out loud, this is the sum over y, the sum over x. Okay, so what is the probability of x equals x given y equals y? Well, that's just going to be x times, this is the probability that x is equal to x, comma, y is equal to y, both of those things happening, divided by the probability that y is equal to y. And then I have to multiply by the probability that y is y. Okay, well, those things cancel, for crying out loud. Okay, so what do we get? That's equal to the sum over y, the sum over x. Okay, it's going to be x times the probability that x is equal to x, y is equal to y. But that's just p of x, y. Okay, I'm going to write that as p of x, y. Okay, so it's p of x comma y, right? We've seen that before. No horsing around here. Okay, so watch this. I'm going to switch the order of the sum. So this is sum over x, sum over y, x, x times p of x, y. But don't you see that you can factor out this x? That x doesn't depend on y. Okay, so this is equal to, let me write it over here, equals sum over x times, or sum over x, x times the sum over y, p of x, y. But what's that going to be? If I add up all of the p of x, y's for a fixed x over all y's, that's just the marginal of x at x. So this is just going to be the sum over x, x times px of little x. And lo and behold, what is that? That's the expected value of x. Okay, so the expected value of this random variable, the expected value of x given y, sort of averaging over all possible y values, I end up just getting the expected value of x. Okay, just get the expected value of x. That's the end of that. Okay, so that's interesting. It's very interesting. So, why does that help us? Well, let's just do an example, and I'm going to finish with this. I'm going to do the hypergeometric. Okay. Okay, so here's an example. So suppose that x is given by the hypergeometric, and what are we going to have here? Well, let's just say that we have, you know, I'm trying to remember what the variables were that we were using before, but I'm just going to make up some other ones here. Okay, so n, this is the sample size. Okay, I have so many good things, so we'll say that capital M are the good guys. Okay, and then you know, n minus m. These are the bad ones. So that tells you that there are a total of capital N things to choose from. Okay, so again, the picture that we have here, there's n total. Okay, there's m on the good side, and there's n minus m on the bad side, and you're taking a sample of size little n. Okay, just to make sure that we're all on the same page here. Okay, so look, let's just let let's just let AI be the event. Okay, thinking of drawing these balls from this urn one at a time. So AI is going to be the event, a good drawn on the ith ball. Okay, and that's for 1 equal to or less than I equal to or less than n. So we think of this as being done sequentially. And the deal is that these are without replacement, right? So without replacement. Okay, here. So AI is, the good is drawn on an ith ball. So I hope it's clear to you that X is just going to be the number of these events that occur. So it's going to be the sum I going from 1 to n, the indicator of AI. Okay, the indicator of AI. Now here's the problem. When we go to compute the expected value of these events are highly dependent of one another. So for instance, A5 really depends, right? So note this, note well, A1 through AN are dependent. Okay, highly dependent actually. So, I mean, I can't really compute the probability of A5 without knowing what happened with the first 4 draws. You know what I'm saying? Because I might sort of deplenish the number of goods, or I might deplenish the number of bads, which might increase my odds on the 5th draw. Okay, so I have lots of dependencies going on here, and that's slightly annoying. You know what I mean? Okay, so here's the thing. So what is the expected value of one? The only one that really doesn't need to be fussed with too much is the first one. Okay. Well, it's pretty clear that that's just going to be the number of goods over, right? So it's just the probability of A1. Okay, which is just going to be you know, the number of goods over the total number of things. It's just m over n. Okay. Now, let me ask you something. What about the expected value of the indicator of A2? Okay, so that's where the problem starts to come into play. Okay, and why we need these other things. What about the expected value of the indicator of A2? The problem is we need to know about the indicator of A1. Okay, I need to know what happened with the first draw. Okay, so that's where we can use conditional expectation. Okay, so this is going to be the expected value of the indicator of A2 given the indicator of A1. Okay. We just got done showing that the expected value of X is equal to the expected value of the expected value of X given Y. Okay. So, what do you think here? Well, look, I can treat the indicator of A1 as if it's kind of like its own constant here. So I just need to let that thing automatically deplenish the good balls. Okay, so look at this. This is going to be equal to the expected value. Okay, look, either the first draw deplenished the good balls by 1, in which case the indicator of A1 would have been 1, or it didn't, in which case it would be 0. So isn't this just going to be m minus the indicator of A1 over, over n minus the indicator of A1? I mean, think about it for a minute. You know, if A1 actually occurred, then the number of goods went down by 1, but so did the number of, oh, actually, since this is without replacement, all I need to do here is just say -1. I know that I'm going to remove whichever side it came from. Okay, but the issue is I don't know, without knowing the value of the indicator of A1, I don't know whether the good side was deplenished or not, which is why I need to do this. Okay, so what is the expected value of this thing? Well, well, let's see. The indicator is equal to 1. Okay, the indicator is equal to 1 with probability A1. Okay, so this is going to be m minus 1 over n minus 1. So this is if A1 happens, and therefore the indicator is 1, what's the probability that happens? Well, m over n plus what? M minus 0 over n minus 1 times, okay, well, what's the probability that that happens? Well, that's just n minus m, right? So that means that a bad one was drawn. There's n minus m of those, n minus m over n. Okay, so what do I get here? I get m times m minus 1 plus m times n minus m all over n times n minus 1. Okay, so what do we get? I factor out the m, okay, and what's left behind? Well, it's going to be m minus 1 plus n minus m over n times n minus 1. Okay, the m's cancel, and it's going to be m times n minus 1. Watch this. M times n minus 1 over n times n minus 1. Those cancel, and you get m over n. What? Okay, so the indicator of A2 is m over n again. So let's keep track of what's happening. The expectation of the indicator of A1, that was easy. That was just m over n. The expectation of the indicator of A2, we had to work a little bit harder, but we got m over n again. Okay. Interesting. Okay. So let's see what happens here. Moving on. What about the expectation of the indicator of A3? Well, the issue is I need to know stuff about A1 and A2 to know what's going on with A3. Okay, I need to know what's going on with those things. Yeah? Okay, so what is the deal? What's the deal with those? Okay, well, watch this. Okay, and we're going to be a little bit more sophisticated this time. So the expectation of the indicator of, oops. Right, we're going to use our formula. So this is the expectation of the indicator of A3 given, now I'm actually going to put the previous two random variables in here. So given the values of AI1 or of 1 sub A1 and 1 sub A2. Okay. Well, this is going to be the expected value of what? Well, let's think about it here. So what is the value of this thing going to be? Well, it seems to me, again, this is just an indicator. So this is just an indicator. So I just need to figure out what the probability of A3 is. But isn't that just going to be m minus right? I just need to subtract the number of balls that were removed from the good side. And I know that it's just going to be n minus 2 balls that are left. Okay. Okay. So it's just, that's what it's going to be. It's going to be the probability of A3 given the values of A1 and A2. Right? I need to average these things out. And watch what happens here. Like I didn't do this last time because I thought it was worthwhile to go through the computation, but you can actually pull out 1 over capital N minus 2. That's a constant. So it's 1 over capital N minus 2. Okay. And what's left behind here? So it's going to be the expected value of M, which is a constant, minus the indicator of A1, minus the indicator of A2. Okay. But that's just 1 over n minus 2. M minus the expected value of A1, which is m over n, minus the expected value of the indicator of A2, that's another m over n. Okay? So look at this. It's going to be 1 over n minus 2 times, okay, let's see, it's going to be n m minus m, or let me just write it this way, minus 2m over n, once I come to a common denominator. So this is going to be 1 over capital N minus 2, n minus 2 times m over n. And what happens? The n minus 2's cancel, and you're left with m over n. You see what's going to happen here? You're going to end up, by using these conditional expectations, you're going to get that the expected value of any of these indicators is going to be m over n every single time. So let me just say that similarly, the expected value, the indicator of any of these, is equal to m over n. Okay, I couldn't just willy-nilly assume that that was going to be the case. I had to know what was going on with the previous indicators to know what was happening. But it looks like that's exactly what's going to work out. In fact, you could sort of prove this by induction if you wanted, right? Try it for yourself. Try the indicator of A4. You could assume that, you know, each of the previous guys has expectation m over n. Then I promise you'll end up getting that the next one will be m over n also. Therefore, let's kind of write out the end result here. Thus, the expected value of x, that hypergeometric, is going to be the expected value, the indicator of A1, plus the expected value, the indicator of A2, plus dot, 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 plus the expected value, the indicator of AN, right, for that nth draw. And all of these are m over n by the trick with conditional expectations. How many of these are there? Little n of them. So you get n times m over n. That's pretty slick. Okay. I'm not going to go any further than that. I just wanted you to see some of the power of this conditional expectation business. It is a very useful tool. I would encourage you to kind of study up on it on your own if you want, but I at least wanted to expose you to it just ever so slightly. And again, you can do a lot of this stuff also with continuous random variables as well. It works out similarly, except you're doing integrals instead of sums. Okay, I think I'm going to stop right there. And the last couple of lectures, we'll look at chapter 8, some limit theorems, including the central limit theorem. Bye for now.